the mask is the see whether no you ask also by the time I also don't know when what's this? Mask dulu, hurry up din. Please din. Oh yeah, yeah. Which part of Tiong Bahru again? Oh, I have one who Tiong Bahru, but she's Sec 4. Sec 4, she's still called Claire from Nanhua, but she's Sec 4. Okay, I'll join on Zoom. Oh. Now then you reply me. An hour-ish. Oh, finally school over. Oh, not you. Yeah. School already ended. Okay, I need the paper somewhere. Shit. Yeah, I know. I would need the pictures of it though. Wait, let me just check whether Estelle sent it before or not. That's the thing. I kind of remember that I have it though, but I don't know why. Don't have. She hardly sends me any question. I might ask Jada. Jada. Hello, Jada. Jada. Hello. Yes, Jada. Hey, do you have the paper? As in, do you have a soft copy of the paper? You have the soft copy of the paper. Oh no. Yeah, soft copy. You have the like did they upload it onto your your class drive or anything like that? Mm-mm. Only have the mark scheme. Okay. Hang on. Okay, where are your problem areas for you? Your MCQ was what? Okay, your MCQ. Do you indicate which ones you got wrong already?
It's on here, but I tried to redo it yesterday.
Yep. So, okay, so which ones are you still experiencing problems with?
There's a few that I don't know why I can't do it.
Okay, can. Okay. Jada, let me okay, I tell you what, Jada, can you help me prepare the paper two by scanning. So you help me take pictures of the paper two, can? While I go through some of the paper ones, is that okay? Yeah. You take picture of the paper one. Yeah, you take now. Like as you take one, you send me one, I start doing and you continue doing it. Because don't have soft copy. I don't have soft copy of your papers. Okay. Okay, can.
Every single page.
No, as in like the ones that you need help with lah. Wait, then you send me the one is what?
The three.
Question 3 ah? Ah yeah, question 3 I just recently went through the class.
Oh.
As in like, I think with one of my other classes. Uh, I, I, I think you scan everything if you can cause yeah. Then I'll focus on the questions that you need in a while. Okay. We start on this one first. Okay. So this one here, when you throw something and the drag force is not negligible, right? As it's going up, right? As it's going up, where's the direction of the drag force? Downwards, right? Okay, so the drag force is pointing downwards. So you see, right? What happens is, drag force air resistance. So what happens is, while I see this working here, right? I don't see you drawing the scenario out. So usually, like if you're learning and you're trying to learn fast, actually drawing the scenario out is much better. So as it's going up, drag is acting downwards. You said it, you could tell me that immediately, so which means that you understand what drag force is, right? It's air resistance. No, it's okay, right? And then what happens is that where's the weight acting? Where's the weight of the weight of the object is acting down, right? To you, that makes a lot of sense. Okay, good. So as it falls, okay, so as on its way up, right? On its way up, what happens to the acceleration then? What happens to the acceleration? What? Okay. I mean, it is decelerating. Yes, you're right. But how much is it? Okay, for an object, right? For a lone object, there's no drag. Okay, for example, if you throw it up and there's no air resistance, right? Only the weight of the object is acting on it, right? What's the acceleration for this object? 9.1. You can tell me it's 9.1. Good. So you know that when it's going up, the acceleration is pointing downwards. 9.1. Now I'm telling you there's both drag and weight acting on it. So as it's going up, how much is the acceleration? Made, as in like, how much is the deceleration? More than 9.1, correct? The deceleration is more than 9.1. So it's like, more than negative 9.1. Okay on this? Okay, good. Then what happens is as this ball falls down, right, on its way down, right? Hang on. Right, on its way down, right, when it's on its way down, let's draw another color here like this. How's the drag acting on it? You see, you can, yeah, so you got quite like a few good basics, right? So the drag acting on it is upwards, okay, but where's the weight acting? Down. So while it's falling down, right? So this time around, as it's going down, it will be accelerating downwards, correct? What will be the acceleration on its way down? What? Less than? Good. All right. So now you know that it's less than 9.1, right? Less than 9.1. So this is accelerating downwards. You see, right? Then the thing is this, right? For the same height, like this, right? For the same height, as you're going up, the deceleration is more than 9.1. As you're falling down, your acceleration is less than 9.1. So what does this tell you about the time? Let's think about the the time taken. This will be a shorter time, this will be a longer time. So the analogy of this I like to use always is like a ball of tissue. If you take a ball of tissue and you throw it up, okay, it will it will decelerate very quickly, but then once it reaches the top and it's falling down, it will just, you know, do that thing, right? So that's what's happening here. So in this case, the T up is less than the T down, all right? Because of the acceleration though. I mean, D's answer lah, right? Yeah, D's answer. It says the net force when the object is moving downwards is smaller than the net force when it, but it's not. You see, the option itself doesn't really paint the entire picture. The option itself is not like doesn't tell you this whole thing here. See, so now you understand, right? Whoa, what is she doing online?
She said 5 minutes.
Where's she? Oh,
5 minutes ago.
she said she messaged who?
She told me, I don't know.
Oh, okay, both of you. Hi Estelle. Hi Estelle. Goodness. Okay. All right. So that's for question 3. I'm recording this. So too bad. You wait your turn. As in like you wait until afterwards. Okay. So the next one will be this question. Right. This one here. Question 5, is it? Okay. So you can tell that you are not resolving the forces correctly. Okay. All right. You are not resolving the forces correctly. So I'm gonna prescribe one thing for you for this, right? Because this one here, obviously I can see there's like, you know, everything done wrongly here. Like I don't know what you're drawing here is, yeah. So what we need to do is you need to learn this thing called vectors, right? Vectors, there's a few concepts for vectors. There's addition of vectors, which I think you know. There is resolution of vectors, which I think you don't know, right? There's the finding the change vector, and there's finding the relative vector. Okay, so there's all these, but these were taught in chapter 1.
Oh.
Yeah, this was taught last year in, I don't know, February, March last year. It was not even this year. But and I don't know whether or not your teacher ever actually went to revise this. So you better ask me for a video of it, okay? For vectors. Yeah, sorry. For both Jada and Letitia, I know you asked me for the for some lessons, but then I haven't sent everything out to you yet. Okay, so you just wait for me because last few days has been quite busy for me. Okay, just very quickly, I can't even see what's the original picture. Okay, okay, all right. So hang on. Is it adjusted until it's just about to slide down? So just about to slide down means that it's not sliding down. All right, it means that it's not sliding down. Means that all the forces that's acting on, thank you Jada, right, that's acting on the block is all balanced. So there is the weight force. So obviously you didn't, I don't know whether you drew the weight force. Did you draw it at an angle, some weird angle? Huh? Or is it vertical? I can't tell. Anyway, I prefer to draw it like this, right? Straight down from the center of the block, right? And this force here and this normal contact force here, right? So there's friction, there's the mg and like that. Okay. There's a few ways of figuring out whether they're balanced, right? You are right to draw it like this, but this was done when we were in secondary school, right? So drawing vector diagram, no, I mean it's still a thing in IB. Sometimes they give you the multiple choice, right? You have to choose, right? Which option is correct. So you may have to know how it looks like as well. So make sure you get the arrows right. So the weight, which is mg, and then the friction here, and then the normal contact force here like this. Oh no, I'm drawing it wrongly. Hang on. Okay, because it needs to be perpendicular to each other. So the normal contact force, okay, the friction, so the normal, this is the friction, right? It's such a way that the mg is pointing vertically downwards like this. So this I mean, if it's an MCQ choice asking you to choose which option is correct, it should look like this. The arrows must point in the same direction, right? Mg is vertical, friction is pointing up this way, normal contact force pointing this way. Okay. But what you're supposed to do is you're supposed to resolve. You're supposed to resolve the forces, right? That means you need to find the component that's perpendicular to the slope and the component that's parallel to the slope. So this one here is mg sine theta, and this one here is mg cosine theta. Okay. And then we understand that after I have resolved the mg, so do you understand that resolution of vectors actually means that you're breaking the vector up into two components, right? Once you have broken it up into two components, it's as though the original component is no longer there, like this. The original force is no. So I've broken it up into two components. Mg sine theta is balanced by friction. Normal contact force is balanced by mg cosine theta. Okay, right. Right. There is an equation for friction which I didn't see you write down, so I don't know whether you know whether friction is this. Okay, right? So you know this one. So that means mu n is equals to mg sine theta, and the normal contact force is equals to mg cosine theta. You may have to make n the subject and then sub it in and then find a relationship somewhere around here. Yeah, you figure it out. I don't know which one is it, but there you go. Sure. So for number 5 done. Next one is what? What's the next one that you have? Okay, hang on. Now, if you have done corrections already or you have redone the paper already, if you know something already, then you just don't ask me to go through it, okay? Because we might be in a rush here. What's this? Restoring force must be proportional to. Okay, so the restoring force, right? Restoring force gives you the acceleration. For SHM, what's the relationship between acceleration and displacement? So SHM acceleration must be proportional to displacement, right, and opposite in direction. Okay, so A is proportional to negative x. The actual equation is A equals to negative omega square x. Do you recall this equation? Right, that's the relationship for SHM. Okay, what this question is testing you on, right? What the question is testing you on is you understanding that restoring force gives you the acceleration. Okay, for everyone here, for what? Oh, what? C is correct. Yeah, why? Yeah, C is correct.
Yeah. What?
So why are you asking this question? You mean you got marked wrongly? Cannot be yours. It's OTAS, right?
No, thought A. Oh, okay.
Were you redoing the question?
Yeah.
Okay, so if you're redoing something, please use another color.
Okay.
If not, it's confusing for you even, right? So, but I wanted to point out this. Now, the thing is, always remember that for SHM, okay, acceleration and um, restoring force always points towards the equilibrium. Always points towards equilibrium. Like the acceleration is always pointing towards equilibrium. The restoring force is always pointing towards equilibrium. Okay. I understand. Yes, we always say that SHM, right, is opposite in direction of displacement. So the thing about displacement is that displacement always displaces from equilibrium. I mean, that's what displacement means. If you push it to one side, either you push it to the left side or right side, you are already displacing it. So what the restoring force or the restoring acceleration does is that it tries to bring it back to equilibrium. That's what SHM is all about. That's what an oscillation is all about. Okay, Ken? All right, good. Next one.
13 is also
Th- 13 is also SHM, and have you sorted it out? Have you figured it out? No? Okay, so you haven't figured this one out. Okay, but I see. Wait, what's this?
It's the energy.
Okay, so it has amplitude A, total energy E, mass is doubled, made to oscillate with same amplitude. What's the total energy after the change? So you did write down the correct equation, which is here, all right? And then you did double the mass, right? You did double the mass, and the amplitude still stays the same, right? Okay, but what you forgot is that omega for a spring mass system is affected by the mass. Because what's the original equation? What's the equation for spring mass system, period? Don't know, quickly check data booklet. If you don't know, quickly check the, wait, hang on, I pass you the data booklet. I need to find the these are all the year. Eh? No. Eh? Oh, no, it's all over there. Eh, somehow they managed to filter themselves over here. This two. This two. Take the bigger one, take the bigger one, take the bigger one. 2 pi square root. What are you looking at? T is 2 pi over omega. I've never seen an equation like that before. What? Do you know what omega is?
Uh, wait,
Wait, is she looking at topic 9?
yeah,
Okay. Spring mass system, does it say spring mass system?
and over K.
Right, square root m over k, right? So what happens is, when you change the mass of a spring mass system, the period actually change. And omega is 2 pi over t, right? 2 pi over t. So if you change the mass, you change the period. You change the period, you change omega. If you change omega, the omega square is also affected. So while you recognize that the mass here is affected, you did not recognize that the omega was affected. And therefore, that's why you got this wrong. So you have to go and try this out on your own again. Okay, I'm just going to point out to you where your mistakes are, right? You go and get it fixed, right? And then you know, we'll be okay. Okay. Okay, Jada has sent me almost everything. Wait, let's see whether I can download everything or not. No, I cannot download everything. Why? Why can't I download stuff? Why can't I download everything? I don't get it. Okay, hang on. So are you gonna ask me the next one? What, the Sankey one? Why are you asking the Sankey one? What? Is it Estelle? Excuse me, Estelle? Why are you asking about this? Oh my God, what's going on? Oh yeah, hey, yeah, I have no idea. No, why is it not 40%? It's 40%, right? You mean 40% is wrong?
Oh, yeah,
Yeah, but 40% is wrong.
yeah. I
I mean, when you don't know it's given to the squares, right? Squares. There's a nice grid square. Even if you okay, wait, hold on. Do you use a ruler? No, even if you use a ruler, it would have been correct.
No, I just
No. I went through this. I went through this during the topic revision. I said you, yeah, I said you have to check the thickness of the arrows.
yeah, I like you get what I mean. Like, I like this is promotion, so this.
Okay, no, I don't know what you mean. I don't know what she means. I have no idea what you mean. Okay, so okay, give me the definition of efficiency. Yeah, you know what?
So this is my
Yeah, I know. You know what?
what is
Yeah, then why you write? You the heck you know?
oh,
How many days of school do you skip last year? Okay, so this is a Sankey diagram. It tells you the energy. Anything that deviates out to the side is a energy wasted. This is useful energy, and you're right. Efficiency is useful over total. So 4 units divided by 10 units, 40% is the answer. Okay, next one, please. Next one. What's the next one? Next one, next one. Wait, what in? Hey, your MCQ doesn't seem too hard, huh? Yeah, it wasn't that bad. Really, it wasn't that bad. It feels a lot like an actual IB paper. The SOTA, the year 5 ones, they got massacred. The Jace and Yenny. Yeah. Yeah, they oh man, they got a bad one there. Wait, hurry up. Hey, you don't slack also. Hey, Letitia, you take your pictures. Eh? No, you're done already?
okay.
Jada needs question 32. Your questions are all after 30. Then after you join me, then you have all these questions coming out. You get it wrong. Oh, okay. Yes, I don't have the paper as well. You got the soft copy? No, never. Right? Esther just woke up. Huh? It's quite early. Please lah, you can wake up for dance, you cannot wake up for physics. Yeah, lah, actually true. Who the heck wants to wake up for physics, right? Okay, sorry, wait, 32 is it? Jada? Wait, no, I got 32 here. They sent 32. Right, the rest of you, any more or not? Like after 30s or something? What? Sorry? You sure you want to use your question paper to send out for
Oh my goodness.
Okay. What's this? Okay, so no, but here's the thing.
What is a
No, the best one is this one. I think maybe you use a question paper. Did she bring a question paper? Did you bring a question paper? Okay, what? You what? Who's that? Oh. Why do you what?
Because he wants to do it and then they want us to bring back our paper one because he thought that we were going to change our answers. So he took it back to Shuki. Then he just
But the OAS is already marked and already printed on the side, right?
yeah.
It's machine marked, right? It's machine marked, right? Yeah, it's machine. What he don't trust the machine? Tell him that I don't trust him. Okay, this one here is resolution. Okay, this one here is resolution. This concept here is resolution. So yeah, to be well resolved, right? When we talk about resolution, right, we have to compare two angles, right? Number one, the first angle will be the angle of the pattern. So imagine one source, right, going in like this, and then it makes a pattern like that. Okay, right? We need to see, right, how wide this pattern is, right? In fact, this pattern, right, we want this pattern to be as narrow as possible. We don't want it to be too wide. If it's too wide, what happens is that if this one is wide, the other one is wide, they tend to overlap. And if you overlap, you can't get it resolved. So we want this to be as narrow as possible. The question is, what is the angle here, right? The angle here will be like the angle. The idea is the angle between the minima and its maxima, right? The first minima and the central maxima. Okay, so we want this angle here, like yeah. I'm just gonna put detail here like this. Okay, Jada, do you understand this angle here? Yes, huh? Okay, good. Then now the question will be, what's the formula for this angle? What's the formula for this angle? It's a small circular aperture, right? So what's that? Say it. 1.22. Walao, the other way around can lambda over b and theta is outside here already. Where all your equations come from? Okay, so 1.22 lambda over b. So you must understand this, okay? If you do something to the lambda or you do something to the b, how do you do anything to the lambda? Lambda is what? Is the wavelength. How do you do anything to the wavelength? Change the source. But that would be a bit weird, right? You can't really change the source, right? You can't make it like change the wavelength it's producing, right? Maybe you can put a filter and then and observe a different wavelength. You understand this? Okay, good. So you can observe a different wavelength. But if let's say you're not doing any of that, then this wavelength is constant, right? So how about this? What's this B then? What does B stand for? What's B stand for? Width of what? Width of the aperture. That means the size of the hole here. You better sit down and remember all these little things. You think you know, but I think you forgot already. Okay, so B will be the size of the aperture. All right. So question, how do you make, I just said that you want this pattern to be as narrow as possible. How do you make this pattern as small as possible if B is the only thing that you can change? Yeah, correct. So you make this B bigger. What happens is that the pattern will become a narrower, right? Narrow pattern. So if let's say you have a bigger, uh, like aperture, right? The pattern will become like this, something like that. You get it, right? So you want it to be as narrow as possible. You don't want it to be too wide, because if it's too wide, then what happens is the other patterns, sorry, the other sources pattern, once it goes in here like this, right? And then there's a chance that they will overlap, right? Because I mean, this is not overlapping, right? But I mean, I'm just drawing it like that, okay? So you want to make sure that each of the patterns are as narrow as possible, right? The narrower the better, because if it's narrow, right, it's confirmed not going to overlap like that, okay? So you want B to be as big as possible. So you want the size of that, you want to be well resolved, right? You want it to be well resolved, you want it to be as big as possible. So it's either this or this now, right? Either B or C now, okay? Then we check this one here, okay? We check this one here. So this angle here, we are trying to compare it to what? We're trying to compare it to this angle here. This is the other angle that we're trying to compare to. All right, we're trying to compare to this angle here, this theta here. This theta is what we call the theta of separation, right? The angle of separation. So this angle of separation will be something like this. So this small d against this big D here like this, right? So in fact, right, what a lot of students get confused by is like, oh, do I have to change anything about the screen to the slit? No, this has nothing to do with resolution. Resolution is you comparing the sources to the slit, and the size of the slit. That's pretty much it. That's what resolution is all about. I mean, and the wavelength as well. Okay, right? So how do I get the equation for this angle here? This angle here, I call it the angle of separation, right? Separation. I call it the angle of separation, right? Yeah, angular separation between the objects. You see, there are two objects here, right? There are two light producing objects here. So what's the angle here? Theta equals to small d over big D, like that. Okay, and your job is to make sure, because this angle here actually affects this angle here. These two angles are the same, right? Alternate angles, right? And your job is to make sure that this angle is always bigger than this angle. Okay, yeah, in order for it to be well resolved. If it's equal, if this angle is equal to this angle, then just resolve, correct? If this angle is smaller than this angle, that's unresolved, because if this angle is smaller, which means that the two patterns are very, very close to each other, the two patterns will overlap, and they overlap such that, they overlap like that, okay? Once they overlap like this, that's it, right? You can't resolve it anymore, okay? So your job is to ensure that the theta separation is more than the theta, it's more than the 1.22 equals to lambda over b. So in most cases, it's always like that. So d over d, sorry, d over capital D, right? D over capital D is more than or equals to 1.22 lambda over b, like that. For resolved, for resolution, right? For resolved images. Jada, okay? Yes, where do you make mistake at? Okay, so you want to increase the distance between the two objects. Yeah, it's a silly question, a silly mistake to make, right? Because I think I know, I think you know this. Nah, B is just the hole, the size of the hole there. B here, this one. Okay, all right, cool. All right, yeah, that's for that. Anything else? 36 and 37, and that's all for her. How about you guys? 36, 37. No more?
What's the last thing? The title.
Can you help me take pictures for 36, 37? Yes. We'll be going on to paper 2 in just a while. For one of the what? Oh, 36. Oi, Ida. Oh, is this what you're asking for? No, no. Then you can you ask me for topic 11, induced EMF, the front part. Okay, so I explain this now. So the coil is like this, right? And it's perpendicular to a magnetic field. So the magnetic field is like pointing this way, correct? Hello, hello. Yes, Wait, Oh yeah, it's got a B in its mouth. All right, so sorry. The yeah. So there's a coil, area 2 cm squared, perpendicular to magnetic field of strength 5 milliteslas. The direction of the magnetic field is reversed in a time of 5 seconds. That means right now it's like this. In a while later, right? In a while later, it's gonna reverse, right, the direction of the magnetic field. So then the new direction will look like, backwards the other way, right? It'll look like this. Understand? So and if you want me to find average induced EMF, right? So the average induced EMF will be something like this. Okay. So what's the original equation for average? I mean, in induced EMF, rate of change of magnetic flux linkage. So you have negative d phi dt, correct? That was the original equation. And then you should understand phi is NBA. I mean the change in NBA, right, over dt, right? Because that's what phi is. Okay. Then the problem is that because they ask for average, average means you just simply take the final minus the initial. So you just take NBA final minus NBA initial, then divide by time. Okay, and then the thing is, so the final is this and the initial is this. So the thing is that they are in opposite directions, so they have opposite direction flux. Do you recall if, let's say, a ball with speed v bounces like, across a wall with like, let's say rebounds with speed v, right? What's the total change in velocity? 2v. Yeah, that's right. No, but the whole idea is that always remember that the change is 2 times, right? The amount. So it's like this, right? The magnetic flux was pointing this way. We need to change it to this way. So the total change is this way and then plus this way. So it's actually 2 times NBA. 2 NBA over T. Right? At least the magnitude of it is 2 times NBA. Are we okay on this? Okay. So 2, N is just 1 because a ring. N is just 1. B is 5 millitesla, 5 times 10 to the power minus 3. And A is 2 cm squared, but you need to convert it to meter square. Your teacher is being an annoying person. All right, so we have to convert that to meter square. As I said, 2 divided by 100 squared. Right, so times 2 over 100 squared. And then divide by T, which is 5. Right? And then we have to hand calculate this thing. Gosh. Right, so the 5 cancels off. And it becomes, I think it's something like 2 times 2 is like a 4 somewhere. I would believe that the answer will be just C without going any further. Is it C? No, but I cancel out the 5. Wait, the answer is not C? It is, okay, it is, yeah, okay, can. I mean, your math is not mathing lah. That means your 5 here and your 5 here needs to cancel out, right? Yes. You have to. What's 100 square? 100 square is not. It's not. But you should get a 4. You got to get a 4 somewhere, isn't it? Like there's only one option with 4 in it. No, I don't. Okay. Firstly, Jada, 10 to the power minus 3 and divided by 100 squared. That's not the same, you know? Like, isn't this 100 to the power minus 2? What's this? Yeah. Isn't it? It's all together times 10 to the power minus 7. Yeah, lah, that's the thing. Don't be lazy. That's the thing about you, right? You want to cancel off the stuff. No, you have to change it to meter square. Okay. Hey, all physics equations are all based on SI units. So that means if you are asked to, if you want to find induced EMF here, you make sure all of them SI units. That means B is in Tesla, A is in meter square, and T is in seconds. Okay, good. 36 done. 36 done. And then the next one will be 37. 37. So it's not that you don't know EMI. You know EMI. It's just your math is not there. Don't try to find shortcuts. Okay, what's the induced current? As it. Oh boy. Okay. Whew. Okay, so I have to zoom in a bit. Okay, this one So this coil, right? This coil is right going in this way. Am I right? What is it experiencing as it goes into the field? No, as in like what does it experience? I mean, if you had a ring outside here and you move it like this, does it experience anything? No. So once it's like partially in, like or going into the field, right? What does it experience? I heard someone say something. It experiences a change in flux. Right. So this one is about topic 11. This is about change in magnetic flux linkage. So it experiences a change in flux. So as it's going in, it experiences a change in flux. There's induced EMF, there's induced current, there's Lenz's law, there's Faraday's law, right? So then the question is, what would the ring try to do? The ring will try to induce a current that will oppose the change in flux. One more time, oppose the change in flux. Okay, oppose the change in flux. So it will induce a current that will oppose the change in flux. Right? Don't use any other words. Just remember that these objects will always go in somewhere. Right? If they're being dragged across magnetic field, right? Whatever they do, they will try to oppose the change in flux. So what is the change in flux? Like these dots. What do these dots represent? What's that? Magnetic field lines, right? They represent magnetic field lines. And where are they pointing? Yeah, they're pointing out of the page, right? Out of page, okay? Right, they're pointing out of the page, okay? So what this coil, as you pull in, right? What this ring coil, sorry, what would it do as you try to pull it in? Is that it will try to oppose the change. So the change is this ring starts to experience some flux that's pointing out, right? Okay, so there's an increase of flux pointing out of the page. So what this coil will try to do, this coil will try to oppose that change. That means it will try to cancel, right, the magnetic flux pointing out of the page by creating flux that's pointing into the page. right? Because that's what induced that's what induced currents do. Induced currents flow so that they can oppose the change that's happening to it.
What is this? Oh, as in the current.
So the field that it tries to create, it will be pointing into the page. So the induced current will be flowing clockwise. So your ring, right, this ring here, right, as it goes in this way, right, it will create its own induced current flowing this way, so that it can create flux lines that's pointing inside to try. Yeah, it's not red story, and they're knocking downstairs. They're trying to like cancel, right, the flux that's pointing out, because it experiences an increase, right? So it's saying like, okay, right, you know what, dude, right? I want to decrease this amount of outwards flux, so I create flux that's pointing inwards. So in order, like, by doing so, right, you will induce current that's clockwise. Okay. Then we use the same logic to talk about how when it's being pulled out, right? So don't mistake thinking that the ring doesn't like flux. It's not that, right? And it's not opposing the direction or opposing the force or anything. That it's trying to oppose the change. So right now this ring is being pulled out of the page, right? So as the ring is being pulled out, right? What does the ring experience? The ring experiences a decrease in flux. It experiences less flux, right? So it's not about trying to oppose the direction. So right now you see, right, this ring as it's going out, kind of like you imagine yourself as the ring, and then you think, oh, I'm suddenly realizing that there is less and less of these flux lines that are pointing out the page. I'm getting less of it. So if I'm getting less of it, what should I do to oppose that change? I try to make more, correct? And if I want to make more, I will have to induce current pointing this way out of the page, right? So that I can create flux lines that are pointing, right, outwards as well. So what the most common mistakes that students make is to think that, oh, I just need to oppose the direction, and that's the answer. It's not opposing the direction, right? We are trying to oppose the change. So this case here, the change is you go in, right? You experience more, you try to oppose that increase in flux that's pointing out. Okay, I make flux that points in. Then this change is, oh, I'm getting less of it. So I try to create more of that pointing out. And therefore, using a right hand grip rule, right, the induced current will be anti-clockwise here. Okay, so this is clockwise, this one's anti-clockwise. Does it help you now, Jada? Yeah, you understand this, huh? Okay. It seems like you got the direction for this one correct, but this one wrong. But I just wanted to make sure that you understand the concept of it, because I'm just afraid that maybe I'm missing something. And you said something like opposing the force just now, so I was like not sure whether you're understanding this. This is truly one of the more difficult parts of EMI, right? One more question though. What happens when the ring is fully inside and you're dragging it? What happens when it's fully inside? So this is a uniform field. It's a uniform field. As you pull this ring across, right? What's the amount of flux that's inside that it experiences in the area in between? Is there a change? Is it constant? It's constant, right? There's no change. So no change means that when it's fully inside this field, there's no induced EMF, there's no induced current. It only happens when you're trying to drag it in and drag it out, right? The induced current only happens when it's like halfway in and halfway out. It doesn't happen when it's fully in, because there's no change. Okay. Now this is for MCQ. Jada has sent me all the paper tools. Ah, thank you, Jada. But I'm not sure which ones you want me to go through. So let's try to catch whatever I can. If I can't, then maybe I'll see. I'll see whether I can find another day. But I think that this paper at least MCQ is worth going through, because it's pretty much like your IB standard. Yes, it is pretty much like IB standard. Whoa, what in the world is that? Okay, this one here. Right, do you need my help for this one, Jada? You need question 6, huh? You? Wait, hang on, the two of you? This one? This one, no problem. You think you get it? No, what do you think the underlying problem here is? Let me see your paper. Okay, no. You sort of, but not really. Okay. All right. I just want you to remember, right, that oh, what's going on? Oh. Ah. Okay, this is the weight, right? This is the weight, and this is the normal contact force. The question is, what do you resolve? Because if you were to see the video, right, when we have an object on a slope, right, we have mg here, we have normal contact force here, and we have friction here. Like which force do we resolve for this object on the slope? We would resolve mg, right? We will split mg back to these two components here. But for this particular case, because you know that's going around in a circle like that, right? You do not resolve mg, even though it's on the slope. You resolve n force. You resolve the n force. You resolve the n force, okay, into its vertical and horizontal component like this, right? Because here's the thing that right now it's a different way of resolving it. You could have resolved the n force to vertical and horizontal also for this one here, but this one here, right, for an object on a slope, we usually resolve the mg because it's easier for us to compare. For this one, it's easier for us to understand because since it's going around in the circle, right, there must be a centripetal force pointing towards the center of the circle. In order to have a force pointing towards the center, or to find the force pointing towards the center of the circle, we resolve the n force to the vertical and horizontal. This vertical must balance the weight. Why must it balance the weight? Yeah, it stays in the horizontal position, right? It doesn't go up or down. So we know that the vertical here balances here, and therefore the horizontal is the unbalanced force, is the resultant force, right? And is the centripetal force, right, that acts on the board as it goes around in this circle. So this is the unbalanced one. So we need to do the resolution, right? The resolution will be uh wait this 90 minus theta, 90 minus this theta. So this n cosine theta, right? This n cosine theta is n sine theta, right? Okay, okay. Then the n cosine theta is your what? Centripetal force. Okay. You need question 6, Jada? Oh gosh, I don't know where 6 is. Wait, I'm at 3. Hang on, I settle her question first. Because at least like you guys are here, I can still. Question 6, is it? What? Why there? Is there a ball there? This one? Oh, not this one? Okay. Oh, the next question. Okay, okay. You don't know how to draw this graph. Okay. Okay, okay, firstly, you're asked to draw what's this graph all about? Electric potential or is it gravitational potential? You got to choose. Which one is it? Huh? No, you don't know. You should know. Is it electric potential or gravitational potential? What's that? Electric. Okay, so you know it's electric potential. Okay, what is the electric potential translated very simply? Yeah, voltage, right? Electric potential is just voltage. So basically, you have to just draw the graphs based on the voltage of the spheres. Now, these two spheres, are they both negatively charged or positively charged or what? What are they? I don't know the question. They're both negative. How do you know they're both negative? Okay, okay. So both of them carry the same charge. Okay. All right. So how many marks is this thing here? 3 marks. Wow. Okay. All right. I will give 5 marks for this though. Okay, because it requires a lot of work. All right. Number 1. Okay. Have you found the voltage of A? Have you found the voltage of A on the surface? Which is how much? No. How much is the voltage? Isn't it just KQ over R? Yeah, yeah. So you calculated it wrongly. No, you can't get KQ over R. No, how much? How much? Don't tell me. You tell me now. How much is it? You got it. All of you got this wrong. Do you use the correct equation? Do you use KQ over R? Do you put down KQ over R? Then why is it wrong? Radius is 10 cm1. Calculate the magnitude. You know why you got this wrong? Okay, hang on, Jada, hang on. Do you know why you got A part 2 wrong? Because they asked you to calculate the magnitude of the electric potential gradient, right? And you got tricked because if you remember what electric potential gradient is, what's that? What's electric potential gradient? Yeah, it's E field strength. And you're supposed to use KQ over R squared to find the E field strength. Hey, Jada, A part 2 is E field strength, right? I know, but now do you know that it's supposed to be E field strength? Do you know? Yeah. So you see, right? That one statement that they're just trying to trick you. That's all. Okay. But you got tricked lah, which means that nobody has found what's the potential of VA now. No, nobody yet. As in, like, do you have enough information to find it? Yeah, no, yeah, I know that one, but that one's E field strength. I want the voltage. Now you have to find KQ over R. Yeah, K. No, yeah, find it. Don't tell me to find it. You find it. I'm asking you to find it. Are you trying to find a shortcut? No, because from the previous part, right? From the previous part, the distance is 25 plus 10. Now I want to find out what's the voltage on the surface. Yes, yes, you have to. Yes, you have to use your calculator, Jada. Don't be lazy. Okay. I don't believe any of you. Come, give me the K. What's K? 8.99 times 10 to the power of 9. 9. 8.99 times 10 to the power of 9, not minus 9, 9. Okay, 8.99 times 10 to the power of 9. Then what's the charge? How much charge is it? 4.5 times 10 to the power of negative 9. 4.5 times 10 to the power of minus 9. Right, then divided by the radius, which is what? Radius is 10 cm, right? 10 cm, so 0.1 meters. Okay, right. Oh, shoots. It's 404 volts. 400 volts. It's 400 volts. Okay, 400 volts. Right. So my point is, they didn't give you the scale. You're supposed to have inferred that this 4 dots here, this was 400 volts. It's negative 400 volts. You understand? You see this now? Jada, do you see this now? Yeah. Okay. So yes, you go and calculate it. That's why I was thinking they didn't tell you anything. All right. But how much charge is there on sphere B? How much VB is there? Is the same charge? Is it the same charge? Same charge, right? But then smaller, right? Okay, then you just do KQ over 0.05. right? Same thing. So you know, so 8.99 times 10 to the power of 9 times what again? 4.5 is it? Times 10 to the power of minus 9, then divided by 0.05. That's 810 volts. I mean, it's about 810 volts. Yeah, 810 volts. So I will count 8 squares: 1, 2, 3, 4, 5, 6, 7, 8, and a little bit more, like that, right? That will be the, that will be, okay, down this line, you see this, down this line here, the dotted line, the surface here, right? The surface here, that will be the voltage on the surface of B, right here. You understand this? And this will be the voltage of A on the surface here. The question is, where's the null point? That's why I say this question is a 5-mark question. But it's still worth it. It's still worth to do because you need to find out a lot of things. But we need to find out where the null point is. So where's the null point? And what is a null point? Where the field strength is 0. Right? Where the field strength is 0. So your job is to go and find out where's the null point. Like I said, it's a 5-mark question. You're supposed to go and get KQ over, that means of A, R squared is equals to KQB over 60 minus R whole thing squared. Okay, I'm trying to find out how far is the null point away from the center of sphere A. Right? Okay, and I do it by equating their field strengths because that's what null point is. Right? That's what null point is. I'm equating the field strength there. All right. Um, isn't it the same charge? They have the same charge. They have the same charge, but they are different sizes. Is it? They're different sizes. Okay. Okay. They're the same amount of charge, but different sizes. Same amount of charge, but different sizes. As in the size. So okay lah, yeah, from the centers, right? Okay, fine. It's a bit strange, but okay, whoa. Right. So 1 over R squared equals to 1 over 60 minus R squared. Like that. You know what I'm saying? Right? And then what's R though? Is it just 30? Is it just in the middle? It's just in the middle, right? Yeah, it's just in the middle. Yeah, it's just in the middle. So R is 30. Oh, I find this a bit strange. Okay. But yeah, I mean the math is the math, right? We can't change the math. So the null point is straight down in the middle, right? Straight down in the middle. And that's where the potential gradient is 0. Yeah, I guess you can. Yeah. Sorry, what? That's exactly the same question that she asked at the same time. But yeah, I mean, I don't know whether you can. I didn't know. I had to find out. Like, I wasn't sure myself. Like, I'm not gonna tell you things like, oh, if it's the same charge, then the null point is in the middle. I don't think I can live with myself for that, right? That's why I had to work it out. Right? I mean, it is in the middle. But now my big concern is this, right? Um, so we know that the curve will look something like that, right? The curve, guys, the curve will look something like this. Wait, don't draw yet. The curve will be something like this. From the surface of this sphere to the surface of the other sphere, it will go up and it will go down. The question is, how high does it go? Right? They don't give a mark for how high it goes. Hey, lame lah, you cannot ask this kind of question and then not you cannot ask this kind of question. No, we're gonna find out how high it goes. Right? We're gonna find KQA over 0.3 because we know that it's 30 cm away from the center of A, right? Like, how much is this? So negative, sorry, 8.99 times 10 to the power of, actually you can just times 2 later. 8.99 times 10 to the power of 9, right? Times 10 to the power of 9 times Q is what? 4.5 times 10 to the power of minus 9. Yeah, minus 9. Then divided by 0.3. So it's negative 135 volts, right? So from this one charge alone at this distance is negative 135 volts. Um, but it's the same amount from the other side because, the 0.3 is the same, the charge is the same, right? It's just that the size of the sphere is different, but the charge is the amount is same. So from the other side, yeah, from the other side, you that means you times two this one. This is 270 volts, 270, negative 270. So you go up to about negative 100, 200, 270 is about here, negative 270 volts. That's your null point, like this, here and here. Yeah. I mean, if you want to ask a question like this, right? I mean, to your teacher, if you want to ask a question like this, you should follow it up, right? It will go up to here and then down here like that, right? Second square? No lah, no lah, no. I can prove to you it's not. Yeah, it's not. It's not the second square. It's negative 270 because from one sphere alone, it's a 30 cm away. The voltage is negative 135. So from the other one, it will be also negative 135. So I mean, Jada told me that the marking point doesn't include like what distance does it cross. Yeah. Okay. But here I am teaching you like how it crosses. Okay. So this question here is very loaded. That's why I say it's not worth 3 marks. It's worth 5 marks, right? But what are the parts that I mean? If you pick out every part from it, you realize that each of the parts are quite important, right? The part where you realize that the graph, both of them are negative, right? So negative 400 on the surface of this one, negative 810 on the surface of this one. You realize that the graph between them is to curve up and down. You realize that the point whereby it reaches right, a maximum, the turning point is where the null point is, and we use equations to find out where the null point is, which is 30. So it needs to turn at 30, right? We also realize a couple of things where the total sum of the individual potentials is negative 270 at the null point, which we calculated it ourselves here like this. So the turning point is at this point here. And lastly, the last one I want you all to realize is this: within the sphere here, you see within the sphere, right? The potential is constant. It doesn't like go to zero or anything like that. That means it's constant throughout. From one edge of the sphere to the other edge of the sphere is negative 400 volts. This one here is also negative 810 volts across. Like if I were to ask you, so this sphere here like this, what's the voltage on this side? Negative 810 volts. What's the voltage on the other side? Also negative 810 volts, right? Which is why inside of a sphere, be it hollow or solid, right? Doesn't matter whether it's hollow or solid, the graph will always cut across, right? Like a volcano, right? Call it a volcano graph, right? So it's a constant value. Can right? I'm have to bring in the rest of the class already. Hang on, a lot of them online today, all fall sick. You okay? I'll go back to school for remedial. Oh, sorry, I didn't see you. Where's Ian? Don't tell me he's sick. Or he lazy. Or what?
In the tab it says
Or what?
in the chain it says
Oh yeah, lah, but I don't know where he is. Yeah. Or maybe he forgot. Is it? Jada, do you understand this now, this graph? Okay, I have only time for this now. I'll tell you what. So it looks like the two of you need to go and do the paper, right? So I want you to go and try this paper again, and I want you to continue asking questions from it. Okay, right? So I think this paper is worth it, but it's just that small things like this, right? I think it's very unfair to ask students to do without the full calculations. So if you encounter any of the problems, you let me know. Then I'll tell you whether or not it has to go in deeper, whether or not the mark allocation is worth the amount of effort that you're doing. Okay?